Okay, well, I think we should probably get started so we don't get too far behind. Welcome everyone to the session 1 project development. My name is Jared Olson. I'm a metallurgist for McClelland Labs down the street here. We've got a good lineup of speakers today. I don't know if anyone has downloaded the Hoover app. Does anyone have that already? So if you don't already have that, you can download it real quick and log in with your email. And we're going to try and use that to ask questions. So you can submit your questions through the app, and then we can, I think we'll be able to put them on the screen even. And then we can ask questions in the audience as well. We're going to try and stick to 15 minutes per talk with 5 minutes for questions after the talk. And our first talk for the day is by Alex Holtzapple. His talk is titled Project Planning and Verification Using MetSim Simulation Software at Brazilian Nickel PoE Nickel Project.
Okay, good morning, everybody. Thank you for coming. Thank you to the organizers and the chairs running the shows here for us. I know it's been 3 years in the making. A lot of effort, a lot of hard work goes into that. Glad that we're all here. To jump in and get started, Brazilian Nickel's PoE Nickel Project. Let's do a quick history here. So it's been going on about 10 years, 2012, 2013, right around there. Brazilian Nickel, or I'll refer to them as BRN, acquired the PoE Nickel Project. We can call that PNP for those that find PoE difficult to say. Well done again. Bought that from Vale, the big Brazilian state-run operator. And at the time of purchase, Vale had run some bottle rolls. They had some information that showed high recovery values for nickel and cobalt. And what we did as the modeling team then, the BRN, along with myself, is we focused the initial modeling on designing the conceptual flow sheet. So how are we going to run the heap leach in the downstream facilities? Moreover, we needed to define a heap leach cycle. And we'll talk about that. This is a nickel cobalt laterite ore. It's a bit complicated, so therefore it needs a complicated leach cycle. We'll go through the details of how we did that. On top of the bottle roll test that we had, we also got some extraction rates for nickel, cobalt, magnesium, iron, manganese. And we'll talk about how we incorporated those into the model. 2013, 2015, BRN refurbished the existing plant when they purchased the PNM project from Vale. There was a plant in place, not fully functional, but I'd say 80%. Maybe that's optimistic. Omar can correct me later. But it was quite large, actually, for a demonstration plant. We were running 30 cubic meters per hour through the heap, to give you an idea. So in terms of a demo plant, quite large. And then 2016, 2017, the fun really happened. BRN built about a 10 to 12 ton demonstration heap in 4 modules. 3 of them actually got completed and ran. I'll show you a picture there and we'll talk about that. And operated the downstream plant. And that went on for about 400 days. And so got a lot of good information. The heap was built with 3 very distinct ore types, I'll call them, really looking at the nickel magnesium ratio there, magnesium being the #1 acid consumer, and then obviously nickel being the primary product. 2017, 2022, so for the last 5 years, feasibility studies have been completed and are still being completed, I should say, for a small scale and a large scale commercial plant. Omar is talking. Omar, I'm going to pick on him a little bit. He's in the front row. He's from their project. He'll be presenting tomorrow afternoon. So I'll leave a lot of the operations talk to him. And then really exciting news, just 4 months ago, 3-4 months ago, first nickel product is NHP. If you're not familiar with that acronym, that's nickel hydroxide precipitate, coming out of a small scale project. So you can see 10 years in the making there, probably right on par with most of our activities. We've got nickel. So conceptual flow sheet, hopefully that's showing up well enough over there. And yeah, that shows up okay also. Ore handling. So this is the ore handling agglomeration, added sulfuric acid and water, and then stacked it on the heap. Again, 3 different modules, about 10 tons. Next to the heap, ILS, PLS ponds, top them up with water. Sulfuric acid is necessary. And then the PLS. PLS would pump to impurity removal, mostly looking at iron, aluminum, manganese. So bring that pH up a little bit, drop as many of those impurities as we could while not obviously dropping out nickel and cobalt. Solid liquid separation to get rid of that solid impurities. Down into ion exchange, separate the nickel and the cobalt, and then each of them went to their precipitation stages. So once again, pH adjustment, precipitate NHP, CHP for cobalt hydroxide, and then send the solution back to raffinate. So fairly standard flow sheet in that regard. Here is a good aerial photo of the shot. This was probably 2014, 2015 when the heap was being constructed. I see Carlos enjoys that. Probably some good memories for him. He's also up here from Brazil, so welcome, Carlos. We see right in the middle of the screen, and I apologize if you're on that side. I just have a tendency to go that way. I'm right-handed. Right in the middle of the screen, we've got the heap. We can see even the berm divider there between basically pad 3 and 4, or what we called heap 2 and 3, because we had heap 0, heap 1, heap 2, and heap 3, and I'll explain why heap 0 was chosen. ILS raffinate ponds here, and then over there on the wall where the green is showing up way off, we've got PLS pond downstream processing facilities that we just showed in the conceptual flow sheet. Okay, and then yeah, just a little agglomerator right there. So that heap leach cycle that we talked about, this is where a lot of the initial modeling was focused. How are we going to leach this so that we can maximize nickel and cobalt and minimize everything else that's going downstream, right? If you're running a precipitation plant, the more acid that goes down there, the more other dissolved metal that goes down there, the more reagents we're having to buy. So what can we do to minimize that? Step 1, let's neutralize. So we take the fresh ore after it's stacked and take the most mature solution out of the ILS pond and leach with that. That would be non-acidified. Purpose of leach step number 1 is, as the name denotes, neutralization. We're looking to remove all the acid if possible. And if we're lucky, we'll even precipitate a little bit of iron if we get that acid down low enough. Lower acid, lower iron, less lime downstream. So it's a win-win there. Secondly, then we'd focus on the primary leach. We would again pool ILS, except this time the ILS is acidified and pretty strong, 50, 60 gram per liter. Those that work in copper heap leaching have no idea what that would look like. So pretty strong stuff. And that reports right back to ILS. So a closed loop on the primary leach. Follow that with a secondary leach. We're pulling from raffinate now, again acidifying, 50 to 60 gram per liter, basically leaching everything that we can, sending that into ILS. And then a wash. If you're familiar with nickel laterites, a lot of people think they shouldn't be heap leached. I remember when our colleague Ann Oxley said they were going to heap leach a nickel cobalt laterite, I said, you're going to build a giant swimming pool. But what that means, there's a lot of residual moisture, 22, 25, 26%. I think we even saw at some points dynamic moisture during the leach cycle. What that means, we've got a lot of dissolved metal in inventory. So process water wash, 5 gram per liter acid, just to keep that pH down. And that would then go into our raffinate pond. So ran that leach cycle on, mostly adhered to that leach cycle for heap 0, heap 1, and heap 2. Heap 0 was a bit of a trial to get us started there. So we take all this information and we need to put this into a model. It is a flow sheet model, which means we have the main unit operations, the main flow streams, the main chemistry. But what we started with is the ore. Let's get the tonnage right. Let's get the metal and mineral grades correct. And because it was just 10 tons, we were able to very accurately separate and identify what the mineralogy was being stacked. And again, heap 0, heap 1, heap 2, 3 different magnesium nickel ratios, really, so that we could sort of see a low, medium, high, if you will, what we expected from the mine plan. And that'll be important as we move through the model. Bottle roll test results, we were able to curve fit and get some extraction kinetics, and we'll start with there, and then we'll change those as we go. Complete flow sheet, as I said, including individual heap leach drainage streams. So again, we've got 3 active modules, each with its own drainage stream in practice. Within the model, we had a drainage stream also for each module. Heap leach parameters, leach cycle that I showed, drainage rates, again, 22, 26% dynamic moisture. We had to take that into consideration, so built that in. And then process chemistry from the heap, we're going to focus on a lot in the coming slides. Impurity removal, product precipitation, that chemistry was controlled by solubility tests, basically solubility versus pH that we'd run at the lab there. The 2 last statements in bold, custom algorithms. That's really what we're discussing here. This is what makes this project unique from a simple simulation model. For 400 days of operation. The modeling team there at PNM and myself really focused on, okay, we've got these extraction rates from bottle rolls from a lab. That's not the case within the heap. Moreover, as the magnesium goes up, how does that impact nickel and cobalt? Or as the acid concentration goes up or down, how does that actually change the rates? So that's what we're going to focus on. The model was updated. It was a trial and error. I'll be honest. We had some ideas intuitively. It's a great staff there, they're brilliant people. But how do we quantify that? That was the focus of the work. So we took heap 0 and we leached it. And we collected the solution and we sampled it and we got a curve. We can see this is, I hope both of those curves are showing up out there. The blue curve represents the nickel tenor from plotted on a scale from 0 to 20. So blue is actual and red is the model result. And we're not forcing that in the model. What we're doing again is we're forcing everything into, so flow rates, acid concentration, et cetera. And then we're having a lot of conversations. I like that 4-letter word work. That's really what went into this. A lot of work, a lot of effort in tuning these. I can't go into a lot of the details on the math of that. That's IP that's owned by PNM and BRN, but certainly happy to talk with anybody offline about that in any way that I can. But what we did then, we had heap 0 and we said, this looks pretty good. We've got a really good correlation here between nickel coming out, and if we've got the flow rates right, the tenors, a good verification with the actuality. Let's apply those same algorithms to heap 1 and heap 2, because there's no point in calibrating heap 1 and heap 2. You can't calibrate it each time. We need to take the one calibrated model and apply that. So we did. And so here we see from heap 1, again, blue line is actual, red line is simulation results. So taking those same quantified algorithms, that same extraction algorithm that we built for heap 0, we applied it to heap 1. Slightly different ore type, lower or higher magnesium, slightly different leach cycle, but the results speak for themselves there. Same thing on heap 2, then just one more curve. Again, red simulated, blue actual. We said, okay, we've got something here. This algorithm is giving us very good results within these limits of magnesium, within these limits of acid. Let's take that and run with it. So how do we apply that? Well, we ran the heap 400 days. We're happy with the model. And we took those parameters and those algorithms and we scaled them to commercial production, right? Heap height was built the same as the commercial, about 4 meters. The heap height in the commercial operations, 4 meters. I'm getting a head nod there. So that wasn't too hard to scale. Algorithm went straight ahead. Same application rate, same leach cycle, same plant. So we had a lot of confidence there going in. We then took the annual mine plan, tons and grade schedule that we were able to get for the commercial project, put that on the front of the model and dynamically run that 20 years of operation and get a plan going forward. We also included site weather data. This is Brazil, but it's the dry part of Brazil. So evaporation, you have a lot of water, it's a problem. You have a little bit of water, it's a problem. Either way, it's a problem. So get that site-wide water balance nailed down. And we did that as well. And then finally, we had some static and dynamic mass balances. The PNM team was able to do some rough equipment size, and I won't say rough, I'll say preliminary equipment sizing with those results, present those to the local EPC down in Brazil, and you saw the history. They're now making nickel. A little bit of verification. Again, the PNM team was nice enough to give me this graph. I don't know if this is the same one that Mark Smith had up yesterday, but I think it's probably similar. It's the same data source. So this is a little bit of verification of what it is that we're doing. This is about 30, 40 days into operation of leach cell number 1 on the small scale commercial plant. So this was from April to May this year. And the purple line there going across 390 days represents the METSIM model's predicted nickel extraction based on the ore that was put in the leach cycle. And we can see the gray line there on the left going out to about 35, 40 days. So very good correlation as we first get started here. Moving forward, what does the PNM and BRN team do from here? Well, we can continually refine the model. Omar and I have had some great talks actually the last couple of days about, well, that mine plan that we thought we were going to have, it's a little bit different. Maybe a little bit more magnesium than we thought, or a little bit less magnesium, or it's just slightly different once you start getting and roll your sleeves up. So we can refine that model a little bit more. When you build these algorithms and anything involving AI, I love that term. I work in the software industry. You got to corral AI. You can't just let those things go in any direction. This model is no different. Each of those algorithms that we put in place, they are corralled with mins and maxes, and where they're applicable, we now need to test those, push those further. And that's part of what the team here can do. Detailed engineering for large scale. That's still underway, I believe. So take that model, continue to refine it on the small scale, and only make that large scale operation that much more robust. And finally, application for additional projects. I know BRN, they're a great company. They're potentially going to expand. They might be buying new deposits out there in Brazil, looking at nickel cobalt opportunities. Let's take that know-how, those lessons learned from doing this, and apply those to another project. Maybe shave a few months off here and there, shave a few bucks as well. So that being said, I do want to thank Omar and Carlos for making the trip out here. Also, thank you to Ann Oxley, who brought me in 10 years ago and kept me around. It doesn't happen often. And yeah, thanks to the Philadelphia Eagles for beating Dallas Cowboys last night. Any questions?
Yeah, my questions are more about your chemistry. Do you happen to know what your carbonate levels were? With this, probably associated both with the nickel and the
That might be a
magnesium.
great question for you guys. What were the carbonate levels, Omar? Yeah, it's pure oxide. That's what I thought. So no real carbonate. Magnesium was definitely the main acid consumer.
But it wasn't a carbonate; it was an oxide.
It was an oxide.
Okay.
That's correct. Yes.
What is your variability of your magnesiums and aluminium, and how does that affect the whole process?
Yeah, variability is, I'd say, substantial. Magnesium can go anywhere from, say, 5 times nickel to 10 times nickel, maybe even more so as we're starting to get into the small scale. And this is where we had capped those limits that I had talked about on the algorithms. They can certainly spread themselves out as magnesium goes up. We know that nickel slows down, but once we get outside of what we had tested, the model does start to veer off a little bit. And this is where the continued refinement of that model needs to come in. But yeah, unfortunately, large variations of magnesium.
Yeah, so will your modeling be able to, when you go into production, will you be able to use the model to adjust for the changes in the precipitates that you're trying to get out?
Yes, sir, I believe we can. That is certainly that first step there. That first bullet point that's on there is, now that we have the small scale operating plant, more data, more information, let's expand those boundaries. Let's let it work outside of the magnesium that we had tested on those 3 modules.
Any other questions? We got a minute or two more.
Really fascinating work. I appreciate it. I'm just curious, kind of going along with the same things being said over there. As you scale up over time, I wonder what sort of history there is going from modeling and small scale production to then modeling and larger production. I know, in larger production, you end up with a lot of things that aren't necessarily anticipated, compaction, channeling, different things like that. I wonder, historically, how well that scales up and how well you think it's going to scale up for your operations as well.
Yeah, great question. And I'll be honest with you, this was really a first of its kind. This type of modeling that was done on the PNM project, we had never had access to go so deep into the chemistry and get so much information out of that size plant. Again, 10 tons and 30 cubic meters an hour gave us a lot of information you typically don't have. So I'll be absolutely honest with you, I've never scaled to this degree. There are ways we've done it in other projects where you're taking somebody with 30 years experience, 40 years experience. I know we have a few of them in this room. Usually I call them and I say, how can I scale this to go from, I think 10,000 tons a day to 14,000 tons a day? I saw a gentleman who would have a pretty good idea just this morning. But no, in terms of this type of model, first of its kind. But I'll keep you posted. Yeah.
Perfect. Thanks,
Great.
Alex.
Thank you.
Our next speaker will be Brittany Garcia from Forte Analytical. And the title of her talk is Metallurgical Considerations for Modeling the Recovery of Gold from Heap Leach Facilities.
See if I can get this switched here. A little too short to see over the podium here. So thank you everyone for joining me this morning. I know some of you may have been expecting Nick. I am not him. So I wanted to go ahead and give you guys a quick introduction about myself. I know a lot of you might not be familiar with me. I'm pretty new to, Forte Analytical and to the gold side of things. So I was born and raised in Saavedra, Arizona. Went and got my bachelor's of science in microbiology from the University of Arizona. Go Wildcats. I am a third generation miner, which is probably no surprise considering I'm from Safford. I got my two kiddos. You can't really see it on the screen. There we are. Okay, cool. So I've got my two kiddos. Damien is 11 and Josiah is 15. And the three of us moved up to Colorado from Safford back in 2020 to help start Forte Analytical. So speaking of Forte, wanted to touch on our Forte family. It has recently grown. We have our Forte Dynamics group, which I'm sure you're all familiar with, our engineering and consulting group. Then we have Open Contour, who is going to be our mine design and our modeling group. And just for heads up, they do have a little demonstration coming up today at 2:00 at their booth over here. So check them out if you're interested. We recently merged with RDI. They are flotation and leach testing in Wheat Ridge, Colorado. And then we have Forte Analytical. We do leach testing and chemical analysis there. So kind of touching on a lot of things that have already been mentioned today with Annie and Ken. They've brought up a lot of these kinds of issues that they've seen firsthand. So going to be touching a little bit more on that stuff, looking at geological modeling initially, looking at the location and distribution of your ore, physical characteristics. So whether you have your grain size, crystal structure, particle size distribution, things like that. Mineral alterations, whether you got free milling or refractory ores. Want to touch on fire assay, looking at total gold and silver content, and then coupling that with cyanide amenability leaching. That's going to be a big one that I want to touch on. That's going to be your actual leachable gold and silver. Going a little bit further, we want to touch on doing total carbon and organic carbon to look at preg rod capacities in your ore, total sulfur and sulfide content, as well as for reagent consumption and other reasons. Of course, mineralogy to look at your clays and other problematic minerals. And then touching on more of the physical characteristics of your ore is going to be your compacted permeability for your geotechnical and hydrodynamic, making sure that your ore can withstand weight, make sure it's able to percolate and all those good things. This is a lot of information, so I'm not going to read it verbatim or anything. I just want to touch on the different variabilities of testing. So we have fire assay is going to be similar to a cyanide shake or a preg rub in the amount that it's going to use. With cyanide shakes and preg rubs, it is performed very differently throughout the industry. So you're going to see a lot of different results come out of those. So I want to touch on why that's a big problem and kind of what we should do as an industry going forward. We should make something that is more consistent throughout. Carbon sulfur testing, like I touched on for LECO stuff, is going to be pretty small sample size. So we want to make sure sample prep was really good. Make sure that you have a really homogeneous sample. And specific gravity is obviously going to give you your density of your rocks. Oh, went too far. Also looking at ICP or element analysis. Again, that can vary a little bit between wherever you're looking at and what you're looking for. Agglomeration, we talked a little bit about it in some other talks. Compacted permeability also was brought up. So looking at ROM size, crushed material, you want to look at all that. Mineralogy and bottle roll testing can also vary differently from what you're looking for. So I kind of want to jump into some case studies to kind of talk on some points that why this is all very important. So we're going to look at our first case study here, which is clay determinations. Something brought up and a few times. So we have our wet screen versus our dry screen here. So if you look, we have dash lines and solid lines. Our dash lines are going to be our wet screen and the solid lines are going to be our dry screen. So anything at 20% or above is going to be considered problematic. So we'll either have to agglomerate or blend or whatever the situation might be. Another thing you want to look at is looking, for example, the orange. I'll try to point at some of them. You have the orange line here and an orange line down here. You can see the massive difference between a wet screen and a dry screen. So you really want to make sure that you understand what you're screening for and make sure that you are looking at both sides of the spectrum there. This is just kind of a quick thing that we worked on with the client. So basically, what this was a question of whether to blend or to agglomerate. Initially, they were planning on agglomerating, but looking at the amount of clays over time coming to the pad, it was determined that it would actually not need to be agglomerated, and that was the agglomerator was removed from the feasibility study. So bringing up what we talked about a little bit before, you really want to make sure you know your ore and what you're dealing with, how it's going to affect your percolation, your leachability and all that. Make sure you're not blinding off the pad and how to best deal with it. The next case study is going to be non-standard analytical. So this is where we're going to start talking about our preg robbing, our cyanide amenability testing. So basically we've done work where we add several different amounts of a gold spike to samples to see their consumption. And it really depends. We found it depends on the amount of gold available. That will depend on the amount of carbon that is, the gold is loaded on the carbon. Sorry. So if we also look at the graph over here on the right-hand side, we have our preg robbing versus our organic carbon content. And what we're looking at here is anything above 20% preg robbing is considered an issue. Forte recommends not dealing with that kind of stuff or having to have a plan on how to deal with it. So if we correlate that, let's see, that 20% preg robbing, that only corresponds in this set of data to 0.1% of organic carbon, which is very low. So for any of my geologists or people who are very well familiar with core, a lot of times the organic carbon is determined, I say determined visually, or it can be at least preliminarily decided as by visual. So I wanted to bring up here, it's 3 different pictures of some core that we had. I would like to actually ask if anybody would be brave enough to guess the content of the first one all the way to the left over here. If anyone would guess the amount of carbon in here. It's kind of fun to see. 0.2, okay, that's a good guess. We got 0.11%. So just a hair above what we determined to be problematic, right? So knowing that one and assuming the dark marbling in the middle one is going to be higher organic carbon, right? You would assume it would be much higher visually. Looking at the second one, it's actually going to be 0.16%. So visually seems a lot more, but both are considered above the amount of organic carbon that would be potentially preg robbing. Cool. That's about right. Does anybody want to take a stab at the last one about how much organic carbon might be in that one? 0.25. Any other guesses? 2. Shockingly, 0.15%. So this just goes to show you that visual determinations are not the best way. It's a good maybe initial marker, but making sure that you go through and do your due diligence and really looking at your ore from start to finish is really the best way to do it. We're going to jump into case 3, which is actually going to be with Fiore. So a lot of this was kind of touched on this morning, but that was a good preface to all this. So we did some work with them where they drilled 15 PQ core holes back in 2020. They did the full length of the deposit. There was 6,201 feet drilled and with a total of 1,366 intervals tested. So we broke this up into phases. So phase one, we did all the things that I said we should, that we said we should do. We should do fire assay, cyanide amenability, look at your carbon, look at your sulfides, look at your elemental sweeps, specific gravity, crusher work index, and mineralogy. With looking at all these things, Fiore has this 4-digit code that they're able to come up with to kind of look and distribute their ore. So you can see that right here in this bottom half, it's going to be based on your formation, your lithology type, your primary alteration, and your redox state. So looking at that, we were able to code the types of ore very easily once we had all the analyses put together. And I'll show you some graphs on how well that correlated. So here we have our fire assay versus our cyanide amenability. And you can see that, I guess I'm left-handed preference. So you can see right here that we have the same set of data on both graphs, but it is broken up into different alterations on the left-hand side and redox state on the right-hand side. So obviously doing that due diligence and understanding the ore prior, we were able to see this come to fruition later. Going forward, this is also the same sets of data points, but now we have it broken up by formation here. And then that's going to be alteration and redox state there. So you can see how well the data correlates all together. Another thing that we looked at was modified shakes. So again, this is a really big issue in the industry is everyone runs a cyanide amenability shake very differently, whether it's a hot shake, 24-hour shake, 1-hour shake, inverted shake, orbital shaker. I mean, the list goes on and on. So this is just a quick reference of how different things can be ran. What we've done here is we did a industry type standard shake. It was 15 grams of material, 2 grams per liter cyanide, adjusted to 10.5 pH, ran for 24 hours on an orbital shaker. And that's going to be your left hand industry shake. We got an average of this data set of 28% recovery for gold. We recognized later that we tested the pHs afterwards and the pHs were very low. So we obviously had some sulfide material in there or something else that was consuming our lime reagent. So what we did is we did the same exact samples in duplicate, but we monitored pH throughout before adding cyanide and continued adding lime until the pH stabilized at 10.5 over time. Once it stabilized, we added our cyanide to the solution and we ended up with a higher recovery of 58% on average. So this is a good demonstration of you knowing your ore and how to actually run the test. When you get the test numbers, what do you do with it? So that's really the main goal here. All right, mine's pretty quick, I hope. So the summary here is to make sure that you consistently monitor your samples from start to finish. Your logging from geological to metallurgical is very important. Taking the time up front to build your database, do your test work, that good work thing, right? You got to put in the work. You've got to do your testing. You've got to know what you're working with. And that way you can hopefully reduce some of the unexpected issues down the line. Make sure it's, like I said, capture and run tests from start to finish. Understand that different types of testing and what numbers they produce. It's great to get a number to run an AA and get some numbers of gold. What do you do with that? How do you move forward with that? What does that mean to you? And then appreciate that each sample, each site, each ore has its own quirks. It's going to need its own database. So making sure that you take the time to do that for each ore that you have. And that's it for me.
Any questions? I was going to ask, you showed a plot of Prague-Rob factor versus organic carbon content. How many different ore types or ore samples were in that plot? And how much variability do you see in that curve when you're comparing different projects?
Different projects is going to vary wildly. That was actually just one set of samples. So one specific ore deposit, one set of samples. I'm not allowed to say who, but it was definitely just a one set of samples. So it will very much change depending on what you're looking at. Yeah. Cool.
Okay.
Thank you.
Okay. Our next speaker is Craig Benson, who's Wisconsin Distinguished Professor Emeritus at the University of Wisconsin-Madison. And he's going to be talking about bentonite polymer composite geosynthetic clay liners for heap leach liners.
It's nice to be here in beautiful Reno. I came from Wisconsin and it was snowing this morning in Wisconsin, so a little warmer here. Switch gears a little bit. We've been talking about geochemistry more from the leaching perspective. Here we're going to talk about the impact of geochemistry on the lining system that sits at the bottom that we're relying on to collect the liquid that we want to process. So begin with that. There we go. So we're going to talk in particular about these relatively new materials, these bentonite polymer composite geosynthetic clay liners that we began developing about 15 years ago, but really have in earnest become in practical application in the last 5 or 6 years or so. And our application to heap leaching applications was really relatively new and something we were exploring as part of this particular study that we did with Solmax. So our basic idea, we've got a heap leaching situation on the left. We've got a liner at the bottom. We're having liquid. Let's see if I can find have our solution that's migrating down through the ore, running on top of our liner, and then we're going to collect it. And of course, if we want to be able to collect that solution and also prevent any impacts to groundwater, we need an effective liner. And that liner may be constructed out of a geomembrane, a high density polyethylene sheet, a geosynthetic clay liner, or a thin factory manufactured clay liner, or typically a combination thereof, where the two materials work together as a composite to create an extremely low leakage rate, minimizing any loss to groundwater and maximizing our ability to recover the solution. For that to work, though, these materials have to be chemically compatible with the liquid that we're trying to manage. And that really is the essence of these particular materials, these bentonite polymer composites. What are GCLs, or geosynthetic clay liners, these thin factory manufactured clay liners? Essentially look like a carpet. We've got two geotextiles sandwiching between them about 4 to 5 kilograms per meter square of granular bentonite. And that's the granular bentonite here. The geotextiles are non-woven on the top. It's got a woven on the bottom here. You can see the dry granular bentonite on the interior, and they'll come in a roll, and we can roll this out at the site. Very quick construction, overlap it. It tends to hydrate from moisture moving up from the subgrade, potentially creating a very impermeable material. For these materials to work, though, that granular bentonite, which looks like sand, it doesn't look very impermeable in itself, it has to transform itself. And that's really where the geochemistry comes in. The product looks like this when it's delivered to the site. We've got that granular bentonite sandwiched between two geotextiles. We're rolling it out in the ground. It has to hydrate and transform itself into a gel like we see down here. And whether that happens or not depends entirely on the geochemistry. It may become very impermeable, like this one that I exhumed from a site in the Sonoran Desert. This had been in service for about a decade, still very impermeable, about 10 to the minus 11 meters per second. But in some cases, we'll have applications where those granules don't swell at all. And it will be very, very permeable and an ineffective barrier. And what's particularly important is that the swelling of these tends to be suppressed in high ionic strength solutions or concentrated solutions. Also, solutions with rich in divalent cations or polyvalent cations will also suppress swellings, things that we would commonly find in a heap leach solution. And just to illustrate this, I did a couple of examples here. I took the bentonite that would be in a GCL, again, about 4 kilograms per meter square granular bentonite, took that mass per area out, put it inside a Proctor mold, 100 millimeter diameter mold, and it's about 6 millimeters per thick dry, so a thin layer at the bottom. And then we pour the solution that's going to be hydrating it on top of that liquid. And we watch it swell. This is an old swell test developed by the Geosynthetic Research Institute about 25 years ago, but really illustrative test. And if we pour deionized water on top of that bentonite, it swells like crazy. This is what we'd expect for bentonite that we would use for lots of sealing applications. In fact, it starts off about 6 millimeters, and you can see this has swollen up to on the order of 40. So it just swells like crazy. Extremely impermeable. Take that same granular bentonite and hydrate it with a 50 millimolar calcium chloride solution. Just change the geochemistry. And it's actually not a very concentrated solution, but a divalent solution. Same amount of bentonite, same mass per area. This is what it looks like. You can see if you look closely, if you got really good eyes, that the granules of bentonite are still present. Their swelling is completely suppressed. This material is impermeable. This material is highly permeable. So just changing the geochemistry, we can have a GCL that's very impermeable or very permeable, depending on the situation. So we were looking at materials that we could use or add to the bentonite to create something that would work under a broad range of geochemical conditions, from dilute monovalent solutions to concentrated divalent polyvalent solutions. And we stumbled on, actually by a mistake we made in our laboratory about 15 years ago, that by adding small amounts of hydrophilic polymer to the bentonite, we could actually create a composite material that would function over the entire range of conditions. And so if we think of on the left with a conventional bentonite, if it swells, the granules swell shut and the liquid has to go through this tiny little pathway. Very impermeable. If the granules don't swell, we'll have a pathway that remains open and it's more permeable. And the idea with these polymeric materials was to add just a modest amount of hydrophilic polymer that would fill that pore space. So we'd rely on some swelling of the bentonite, and then where we had any remaining pores, we would fill that with polymer. And that's what gave birth to the bentonite polymer composite geosynthetic clay liners that are on the market today. So we had used these for a number of applications, largely in other types of mining applications and coal combustion residuals, some other types of hazardous waste where we had strong liquids, but we hadn't used them in this particular application. So we studied it in this particular project to evaluate how it might work, particularly for acidic copper heap leach solutions. Just to give you a sense for what the materials look like, that's very simple. We've got a granular bentonite on the left. It's a conventional bentonite that would be used in a geosynthetic clay liner. And then on the right, it's a commercially available hydrophilic polymer, and that you can buy from just a conventional manufacturer. These two are blended together using a screw auger. You've got a screw auger and distributor bar on an assembly line. You've got two geotextiles that are running across with the bentonite and the polymer being laid down in between. They're brought together and then they're needle punched to create that carpet-like product that you saw earlier. This is what these materials look like when they hydrate. This is an environmental SEM on the left, or a wet scanning electron micrograph. You can see the bentonite granules here that have hydrated, and then you can see the polymer that's bridging and filling the pores between them. And on the right, you can see a photograph of this gooey, sticky stuff. That's the hydrated linear polymer with the gray bentonite in the background, or partially swollen bentonite granules. And it's really this clogging of the polymer filling those voids that makes these materials impermeable. So we wanted to evaluate how well they would work for a copper heat bleach solution. So we took 4 different commercially available bentonite polymer composite GCLs. We created a synthetic solution. I'll show that on the next slide. And we ran tests in this device called a flexible wall permeameter, shown here on the right, which is just a vessel that allows us to apply a hydraulic gradient through the GCL vertically and to change the overburden pressure applied to the GCL through the cell pressure, that liquid-filled cell. And there's an ASTM method for that, D6766, and we followed that method throughout the different testing program. We ran the tests under 2 different conditions. A low stress test, which is pretty typical in practice, it's conservative. And then a high stress test where we actually put a high load on the GCL first and then began to permeate it, simulating more like what we might see in the field, where we build a liner, we put the ore on top, and then we begin leaching it with that overburden pressure in place. And we ramped all the tests up to 600 kPa to simulate different ore thicknesses that we might run into in the field. These were long-term tests, something I'll come back to at the very end. We started these 2 years ago, and we're finishing the last ones now. All right, so they've run almost 2 years. Most of them took about a year to complete. So these are really long-term tests that come to geochemical equilibrium. The permeate solution we used, we looked in the literature for different copper heat bleach solutions. There's a good paper out of the Colorado State group here on the geochemistry of these solutions. We picked a solution that kind of represented an average condition, shown over here with these constituents, is about 700 millimolar ionic strength. And for bentonite materials, there's really 2 key variables that influence whether they swell and their hydraulic conductivity. One, the solution ionic strength, how concentrated it is. And then this other parameter called RMD, which is the ratio of monovalent to polyvalent cations, essentially a relative measure of the relative abundance of monovalence and polyvalence. And this solution was about 700 millimolar, so pretty concentrated. It's got an RMD of 0.2. RMD has weird units of molar to the 0.5, but that's a divalent solution, not surprising given the geochemistry of the constituents in our mixture. It's sulfate predominant. The anion ratio of chloride to sulfate is about 0.6, and then it's acidic as we'd expect. It's pH 2.2. And we ran these tests, as I indicated. We started these about 2 years ago. Most of them took about a year, some took up to 2 years. What did we find? First of all, we did tests with a conventional GCL and with a bentonite polymer composite, 4 of these bentonite polymer composite GCLs. The first thing that we found was with the conventional GCLs that they were very permeable. The solution is just too strong for conventional bentonite. So a conventional GCL that you could buy from a manufacturer is not going to function in this application. And that was true whether we started with a low stress test shown here. These are the solid, and then the high stress tests with the open circles. They were all very permeable, a little less permeable with high stress, but still far too permeable than we would prefer. We'd like to have our hydraulic conductivities be below this orange line here at 10 to the minus 11 meters per second. So you can see we're nearly 1,000-fold too permeable with the conventional GCL. The BPC GCLs, on the other hand, were very impermeable. We saw in our low stress tests 2 GCLs, the red and the blue here, A and B, that had very low hydraulic conductivity. And this is really drips per week, actually, of liquid flowing through these systems. Very, very impermeable. That met our standard. 2 that were just above These were the low stress tests. And when we ran the tests with the high stress tests, all of them were below. And in fact, with the high stress test, we always got lower hydraulic conductivities with a high stress test, largely because we had compressed that system before it had ever been contacted with the heap leach solution. So these materials look like they work well. Some work better than others. Some are a little too permeable. As an example here, C and D, we're a little bit above our standard. And so matching the product to the solution is important. Matching the stress condition to replicate what's going to occur in the field is important as well. You can see we got different outcomes with different stress conditions as well. One of the challenges with these tests, though, is that they take forever to run. Literally a year to get test to equilibrium. Some of these taking 2 years, and not too many projects I'm involved with want to wait 2 years to get a test outcome. Usually I have somebody saying, can you give it to me tomorrow? And we've been working on some index tests to be able to do that. A swell index test, which is conventional for sodium bentonite GCLs, turns out that doesn't work very well at all. Right. The one that we use for conventional GCLs doesn't work. We've been looking at this active water content test as well. We'd like something that we can run in a couple of days to get a sense whether it's going to work or not. We're not quite there yet. This active water content test does seem to be a discriminator, whereas our swell index test really just gives us a bunch of noisy data. So sometimes you'll see that in the literature, people suggest using a swell index test to run a quick experiment to determine whether these materials will work, and just a caution, they won't, but we're working on some index tests that will. Just so some key takeaway messages: the conventional GCL is strongly influenced by the geochemistry, and really they're too permeable for heap leach solutions. The BPC GCLs can work. We want to match the GCL with the solution. We are going to have to do testing to demonstrate that it works, and be prepared. It takes a long time if you're going to be using these materials. 6 months to a year is not uncommon. And hopefully in another year or so, we'll have some type of index test that you can run on the bench in a couple of days and get a good sense of whether it's going to work, to justify a test that runs for a year to find the outcome. All right. That's my last slide. Yep.
Has there been any investigation into how these polymers affect shear strength?
Yeah, really good question. Have people looked at the influence on shear strength? And actually, we just published a paper on that. One of the challenges with these polymers is that they tend to elute out of the system under certain circumstances, and you'll get actually a thin, almost a slippery film between the layers, and that can reduce the shear strength, and is something that needs to be evaluated. One of the solutions to that has been to add another layer of slip film geotextile on the interior of the GCL, which eliminates that migration of polymer out and seems to have resolved that problem. But for now, you have to really test the particular product to make sure that it's going to have the adequate shear strength and not have a problem with that weak interface, because some of the early cases did. Yeah, good question. And if you're interested, and I have a paper on that just came out recently.
It's an interesting product that you've got there. I was just wondering whether you actually had a look at bentonite as a calcium bentonite and what that effect was, because right now you're using a very strong acid solution, and a lot of the GCLs are used in a gold application, which is a very high pH, and what effect that has on your testing.
We have we've looked at other types of bentonites. We tend to use sodium bentonites, particularly in North America, when they're abundant. But because they're sodic, they swell significantly and tend to have low hydraulic conductivity. But you probably could make these materials out of a blend of sodium and calcium bentonites. And to look at that, the advantages of that would be something to explore. We have looked at these particular materials under very alkaline conditions, not for gold solutions, but more for bauxite, for red mud applications. And some of these are very effective with those very alkaline solutions, we did some tests for some projects in Australia and South America with pH 14, just really alkaline solutions, and they worked well with the sodium bentonite as the base material in the polymer.
Great talk, Dr. Benson. Any ideas to the longevity of the polymers?
How long are they going to last? Whenever you use plastic, that's always the question, right? No, it's a great question. We've been running long-term experiments at elevated temperature, essentially trying to accelerate the polymer degradation reactions, doing actually a series of temperatures so we can use Arrhenius modeling to do time temperature superposition, extrapolate out. That's been modestly successful. We should be able to get 100 years out of these materials from what we've been able to tell, but it's going to be influenced by the geochemicals, particular geochemistry that we're going to be applying. That's probably the next chapter that we got to figure out. Pardon me? Yeah, good question. The interactions are more about polymer degradation from interactions with the solution and not from biological interactions. The biological interactions are trivial compared to the geochemical interactions. Yeah, good question.
Is this on? Can you hear me? Yeah, okay. Real quick. So I'm trying to understand, is the polymer filling in the voids between the sodium bentonite? Because the sodium bentonite's still not swelling with the chemical, right? So could you use this polymer with a sand and just.
Yeah, this is another great question. If the bentonite doesn't swell at all, why do you need bentonite, right? Couldn't you just use sand or something that's perhaps less expensive? There is a binding between the mineral surface and the polymer that occurs that prevents elution, which is important. We haven't been able to quantify that in a significant way, but with a non-charged mineral surface, we don't get that same bond. And so like we've done tests with a sand and a polymer, and the polymer will tend to elute out pretty readily. Whereas with a clay, we get some fixation between the two materials, and that prevents elution of the polymer under a hydraulic gradient. I think I'm getting chased on. Thank you.
Thanks for that. Our next presentation will be by Andres Leon Saavedra. This is going to be a virtual one. And his talk is called "At the Limit of Overliner Material Properties Applied for High Capacity Heap Leach Projects." And Andres is a senior consultant for and owner at Axios Engineering.
Okay. Thank you very much. It is possible you can see my
We can see your screen
my
and hear you.
presentation.
Yep.
And hear me?
Yep.
Okay, that's great. Okay, I will try to turn on my video. Is it possible to do it? Give me a second, please. Okay, that is ready. Can you see me now?
We can see you.
Okay, that's great. Okay, good morning to everybody. It's my pleasure to be here and to share about this study. In this case, virtually. It was a pleasure to try to be there, but for personal reasons, it wasn't possible this time. But with the help of the what we learn about this pandemic, COVID pandemic, to use this type of technology to be and this way too and participate. So it's a great opportunity to be here. So in order to the time is which is short, I'm trying to go fast and focus on the main things of what I want to present this time. Okay, so as introduction, overlining materials in heap leach projects, it's very important and means a considerable part of the capital cost expenditure for this type of project. And depending on the location, sometimes represent a big challenge to have a level of enough material source capacity. And this presentation includes two recent studies what we developed for one of the biggest copper heap leach operations in Chile, consistent in one expansion for a secondary leaching process with more than 168 million tons capacity and 120 meter maximum height of the leach ore deposit and a low-grade oxide plant leach expansion of 85 meters high, with a great demand of overlining material where natural sources are almost unavailable. Okay, this is general view of the site of the project. As you can see, we have here a primary leaching operation in a heap leach and on-off path type of leaching process. And after the ore is leached, here is reclaimed and taken out and dampened here in this dam for a secondary leaching process. So this has all this area has a liner system, drainage pipes to recover the solution and have some marginal recovery, and sending to this again to recirculate the solution to the primary leaching process. And then this has been with different expansion phases since the year of this, since 2000 year. So it has been like 22 years in operation, this dam here. And also additional project like a dam leach here for a run of mine low grade oxide ore was developed, and this study took these two different expansion phases here, one for this deposit and another one for here, and in this area for this expansion we have around to 1 million square meters of expansion, and here is like between 500, 200, 600 square meters. So that means like approximately needs of 1 million of the cubic meters for overlining material in an area where they have a lack of natural source to get it. and very complicated about the permitting to get the possibility to extract material from natural streams and natural areas with a lot of environmental protection the last years, because it had been like more than 20 years in operation, and during these 20 years the situation in terms of environmental limitations, it had been increasing. So the operation was needed to explore different alternatives in order to try to get the materials and optimize the use of them, like to reduce the thickness and reduce the process to produce the material. So for instance, here for this area, it was developed like two types of different overlining materials. As you can see, the gray areas here represents areas that are a very good selected and processed material for drainage mainly, and the other areas are different type of material with less process and only probably focus on to get protection to the liner system. This is in order to optimize and try to reduce the amount of material that need to be processed in order to get a very good drainage in general. Well, same here in this case. Well, taking on that, the operation was trying to look for different alternatives between the materials that they were or they had available between them. For that reason, in previous studies was developed or was determined to reuse the same ore leach ore from this secondary leaching. Okay, well, in summary, the operation will start to look for between the same materials in there. So they look this all leach ore dams here as an alternative to use this material as overliner and try to get with the less process possible to use this. Okay, so methodology to determine and this possibility was the use of the large-scale puncture test, and that was developed in collaboration with the Laboratory of Geologic Associates from California, Grass Valley, California. And the test, well, I'm not going to detail about this because probably it's well known about this type of tests. They used to be used a lot to improve the capacity of the liner and for a vertical load for the resistance, and see if there are some puncture. And the important things are, in this case, the test was developed at the beginning for an equivalent height of 120 meters, and we took the overliner samples, same overliner samples that they were trying to use, and put in some density related to 1.85 tons per square meter and a moisture content of 3%. Prepared subgrade conditions that no gelling was say under pressure, and the coarse material large than inches were in contact with the geomembrane during the test. So for the first study related to increase in oversize the material content of the overliner, that's because the additional funds of source to get the materials presents a core size overline between 2 inches to 3 inches. And the project originally was developed or specified for an overliner with 1.5 inches, like a maximum particle size. So instead to they evaluate the cost to process this to get the maximum size of 1.5 inches. The idea was to try to see if it's possible to put just as it is, taking in consideration that they have a lot of approximately 40% of the course that was over the 2 inches. So that means a high cost of selection process. So see if for 120 meters, which is the maximum height for the design, the 2 millimeters HDP geomembrane is able to not have any puncture. So test was run in order to have some restrictions for the material over the 2 inches with just 5% of coarse content. And in this case, the material had 60% under 200 CIF. Probably not is an issue because the material was just taken in consideration for protection, not necessarily for drainage in this case. So here is a picture with the sample in the box for the large scale test. And the results here is showing for this 2 millimeters HDP geomembrane that no puncture failures were observed in the geomembrane, and only small yielding areas that for us is a normal response to the low level reached at this case. In the second study related to the puncture resistance versus a load increase, that was because in parallel, the operation looked to reduce abandoned phases of the deposit to load additional fresh ore. So the objective was to determine the maximum height of the leach ore deposit that can reach to avoid damage in the liner system and the drainage pipe due to the overload. The integrity of the liner material was analyzed, performing different large-scale testing using the overliner material of 2 inches maximum core size in this case, and normal stress increments up to 225 meters of height. In this aerial view, we have the deposit and the operation that are starting to put additional layers of the leach ore here. So to do that, we took the topography, the most recent topography, and revealed with very old information that was what was the original configuration for different phases here. We are talking about that 6 phases here only, and with different type of thickness in this case of geomembrane that was built. In this case, between 1.5 millimeters, 2.5, 2 millimeters, and 2.5 millimeters in these areas. And over this was the projected the additional layers of leach ore to put in there, with the stability analysis also were determined the maximum areas that were possible to do it with not affecting the global stability, and determine the maximum heights for different areas and the different thickness here, and perform the different tests for this different stage. So same literature material of the previous study was used, just taking in consideration the maximum 2 inches as a maximum particle size. And this is a material that looks very, very aggressive in this case, in contact with the geomembrane. And the results for each stage are the following. For the first, we have between 140 meters to 165 for each of the thickness here. And the results looks mild gelling and no puncture were served. In the second stage that we are talking about, heights between 185 and 180 meters for 2 millimeters and 1.5 millimeters. Results shows mild to moderate yielding in this case, as you can see in the pictures, but not puncture were served. And the final stage that we're talking about, but that more than 200 meters, in this case 235 and 225 for 2 and 1.5 millimeters respectively, major yielding was observed, but not puncture was observed as a result. That was a surprise for us because actually we were looking in this test, we were looking the maximum, we were looking the maximum height that to try to get actually the puncture failure, and it was not possible. So we ended the test at this time. And conclusion for this case were, in the case of the first study, because that was only for the case of 120 meters maximum height and 3 inches as a maximum size of the wall liner, will not generate punctures in this case for that type of geomembrane. But for that, the portion of 3 inches core size should not exceed 5%, retaining on 2 inches sieve. And the material must be well graded with sand and gravels content to avoid migration of fine particles from the ore during the leaching process. In the second study, the punctures test results showed for height of 185 meters for 2 millimeters, 180 meters for 1.5 millimeters, showing mild to moderate yielding, in addition not generate any puncture failure. And over 200 meters, major yielding was observed, but not puncture was observed in that case. That because I actually was surprised. And so basically we proved that it is possible to think or maybe to take out the paradigm about the specifications or typical specifications we use for projects in terms to the overlining and protection to the geomembrane of the liner system, and also that when the natural sources are not available, as in this case, alternatives such as waste rock or leach ore can be used as a proven option with less selection process and costs. Some limitations of this study, their analysis were based on the integrity of the liner system under higher vertical loss and did not evaluate a specific variable of each project that may affect its overall slope stability that need to be assessed, of course. And the original project was developed 20 years ago, while the geomembrane tests for this study were of current manufacture. So the probability where materials development are delivering a better performance than before. I mean, than 20 years ago. So thank you for your attention, and I don't know if there are questions related.
Thanks, Andres. Sorry about the technical difficulties. We're a little bit short on time now, so we're going to have to skip questions, but we can get you guys in touch with Andres if you have any questions. Our next speaker is going to be Philippa Killian from Freeport-McMoRan, and she's going to be talking about new projects, review of Lone Star leach pad design.
Yeah, we had to make some slight adjustments for my minimal stature. Okay. So today I'm going to talk to you and summarize the design, construction, and operation of Lone Star Pad in about 15 minutes, which is kind of challenging. So I'm going to talk quite quickly. It's going to be pretty high level. So if you'd like more details, please refer to the paper that we submitted to the conference. Next slide, please. The monitor's not working down here. Okay, all right. So Suffolk Mine's one of the highest producing copper mines in North America. And Lone Star is our newest crush leach operation in Freeport. The pad is designed to hold the Lone Star pit ore, which is some of our highest grade material that we've identified. Construction began in June 2018 when we completed construction in June 2020. First ore was delivered to the pad in February of 2020, actually on Valentine's Day, so I always remember it. The ore is very low acid consuming. It's oxide, mostly chrysocolla, so our best recovering ore. So previous ore at Saavedra has been high calcite, high acid consuming, all the gangue acid consumption predominantly from calcite. Yes, we had good grade, but it wasn't good enough to, so the biggest proportion of acid consumption was the gangue mineralogy. So it's mostly andesite mineralogy. So moving on, looking at the map, let's see. So Lone Star Pad's pit's way over here, and we haul the ore 8 miles to our dump crusher over here. This is like an overview of the whole site. Our two former pits, Dos Pobres pit and San Juan pit, are over here. These were all a very similar oxide, but lower grade, combined with a small proportion of sulfide. And then we convey the ore down the side of the old existing, what we can now call the Saavedra pad, which is phase 1, phase 2. And then we built a new conveyor route over here to convey the ore down to the new Lone Star pad, which is here. We have our SX plant here with overflow ponds for process solution right here. And we also have an acid plant on site because, as I said, we're a very high acid consuming site. So we actually burn sulfur to make acid on site. Next slide, please. So here's a zoomed in view of Lone Star. You can see the conveyor comes down this side. And then we have a series of portable conveyors that convey the material onto the pad. On the south end of the pad, we have the collection tank, and I'll zoom in on that here in a minute. And we have 2 overflow ponds, which we'll look at. So next slide, please. So for design and construction, the pad was designed for a height of 350 feet with 3 phases holding up to 1.6 billion tons of crushed leach ore. Phase 1 comprises of just 10 lifts, ranging from 16 to 20 feet to hold 182 million tons. The pad line is comprised of low permeability material, so compacted clay, which is pretty typical, and an LDP geomembrane, and 2 feet of crushed material and 2 feet of ROM material. And the ore, as I said, is stacked on pad with a conventional conveyor stacker system, which includes an overland pad conveyor down the side of the pad, and then portable grasshoppers and radial stackers. Next slide, please. So construction, again, at the top right, you can see typical construction of our liner system. Clay, geomembrane, underdrain piping, which is in the ROM and crushed ore layer. And then if you look here, these are the way the pipes sit. They go longitudinally through the pad, north to south, and 2 systems of collection pipes. I think there's 11 of them under there. They terminate here in an underdrain sump. And then from there, they're underdrained into our PLS tank, which is right here. Excuse the shaky hand, I apologize. And this is a little zoomed in version of our collection system on the south end here. We also have 2 overflow ponds. This is the process solution pond. So PLS that comes out of the pad gets, if we have process situation, it would overflow into this pond. We'll talk about that a little bit more in a minute. When we constructed the new pad, we used pretty much all the old conveyor system and added a couple of pieces. Pretty much everything was reused. So the PLS exits the pad and converges into a sump with underdrains. Then the flow goes to the PLS tank, as I already said. And in an upset condition, the PLS can overflow to these containment ponds. This is the process solution. This is called the stormwater pond. And there's a little bit closer view of the PLS tank. You see how the PLS lines drain into the PLS tank. We have emergency power here too, generators. So, let's see. So under the pad we have, can we back up one slide, please? Under the pad we have a series of 4 and 6 inch diameter perforated piping, which collects the solution, and it conveys to bigger piping at the front of the pad, and it's approximately, I think it's 24 inch piping at the front of the pad. Can we move to the next one, please? So as we saw, the 2 big storage ponds, they're designed to contain a 100-year rain event. And Saavedra zero discharge facilities, everything that we utilize, everything that touches our process is recycled in some way. The system we had designed around the pad channels stormwater around, so it doesn't contaminate our PLS or dilute it. And also the turbidity that rain would bring with it is also channeled to the ponds, so it doesn't affect our process. And then if in those upset conditions, we'll store PLS, turbidity will settle out, and we reuse that water as we need back into our process. The pad has a slope north to south of 1% and west to east of 2%. And that helps with our drainage. Let's move on, please. Moving on to operations and stacking. The ore is crushed to a PAD of 0.58. We agglomerate with acid and water, so sulfuric acid, which hence the need for the acid plant. And then the ore is conveyed to the pad, stacked east to west. And in preparation for stacking, we strip, we rip, and prepare the area. And we do other activities, which we'll talk about later. The surface is slightly graded, and we use it. Everything is low ground pressure equipment. Nothing over 5 psi goes onto the pad. For obvious reasons, we're all familiar with compaction and porosity, which affects copper recovery, etc. And we'll talk about the geotech constraints a little bit later. Okay, next one. So here's an overview of the stacker. As you can see, it's comprises of radials, and then we also have, grasshoppers, typical grasshoppers, and then you have a radial at the end. And we radially stack and we retreat stack so that we don't compact the ore. And the ripping is done at the very last minute, right before the stacker goes over the ore. It's typical arrangement. I think you're all pretty familiar with this. Move on, please. Again, here's a little bit more detail with the stackering equipment identified. Next, please. So as regards leaching, so phase one of Lone Star operates to a maximum flow of 36,000. Initially, we started at that. Obviously, due to lift constraints, as the pad gets slightly smaller each lift, it has declined slightly. A recipe for leaching the pad is actually in my paper. It's not in the slides, but was determined through several phases of column testing, during which we identified improved acid consumption equations compared to our original pad, which was obviously a very high acid consumer, and we had to compensate for the calcite that was in the pad. We identified our optimal lift height, which is typically 16 to 20 feet. We started our first lift at 16 feet, but we included the 4-foot ROM overliner and made the decision to, based on column testing, to leach it all at once. And we didn't pre-neutralize our high acid consuming or potentially acid consuming ROM layer. It was very successful. We'll talk about that a little bit later. This time, obviously, lower acid consumption from gangue mineralogy, but we have a high grade, so it's a still high acid consuming ore. There's virtually no calcite in Lone Star ore. We hardly ever see less than a fraction of a percent. So the recipe enables optimum recovery in our first leach cycle, and it aligns with our kinetic recovery curves, which is a total of 450 days. Next one, please. Here's a typical example of our leach pad layout. We started with 18 cells. Currently, we're at 17 cells, which are the working from south to north, sorry, cell 1 through cell 17, and then modules A through J or A through K. And we're currently at 10 modules wide by 17 cells north to south. Next slide, please. Here's a typical example of how we actually monitor and control our pad. We have on the right-hand side of your screen, you have the feed skids, which we can control pressure and flow to every single module on our pad, and data comes back to us electronically. And on this left-hand side of the module, you can see the orange areas. Those are flushing skids. We're able to flush every single module twice a day, electronically, remotely via solar power, radio controlled. The main feed lines are 12-inch HDPE feed lines with a dummy line on the other side. The 4-inch PVC actually connects the modules and the skids together. We use drip line to feed north just across the pad. Module sizes were optimized based on previous flow testing and operation to ensure even flow across the area. And module flow feeds from the center, from the skid onto both sides, so we get more even distribution than feeding from one side. Let's see. Everything's battery controlled. Obviously on the leach pad, you're familiar with that. So we're able to control the flow and monitor the flow all remotely by radio communication. We have 2 radio systems, one for the flushing system, one for the instrumentation system. We flush every valve on our flushing system twice a day to ensure plugging. By doing this, we've been able to run much higher turbidity through our SX plant and to the leach pad without having significant plugging events. And then we also put solution on all our side slopes. Every single lift, the side slope gets leached. It's usually put on about a week or so after the surface is put on. So we don't leave anything unleached. Okay, next, please. So here's an example of some of our flushing and feed skids. Top one is our feed skid. So it has pressure and flow monitoring and telemetry back to us, so we know what's going on. And then the flushing skids on the bottom has 2 valves, one for each side of the leach pad module. So moving on. So the controls and monitoring. Here's an example of a typical daily report. We generate a lot of reports around our leach system, so we're able to do that based on all the data that comes back into Pi and into our process control and databases. So we generate a daily quality score. This is just a typical example. We aim for 93%. It varies depending on the lift and everything, but typically, so if this is a particularly good day, we're typically 95 plus. Green means good. So, and that's plus or minus a little bit higher, a little bit low would be the coloration if you look at the scale. So it's flushing quality and solution application rate is monitored daily and during the shift by our water balancing crew using tablets. And they can adjust the flow in the field using the tablet information so that they can dial this in to be this accurate. And they're given the quality score each day, and they're quite focused on their quality scores, by the way. It's a good metric. At the same time, we also generate a geotechnical report, which shows anything that's not acceptable from a geotechnical perspective based on our geotechnical KPIs. And I'm not going to go into these in this presentation, simply because another group is giving a separate presentation on that. Any modules that exceed or have high application rates that could be a geotechnical issue, those are immediately corrected that day. And then to prevent preferential pathways or channel in the stockpile, we step up all our flows incrementally day by day. So it takes us typically 4 days to get to full application rate. That's to, again, obviously you don't have channeling. And we also use drones. We've implemented drone technology about 2 years ago. We use them to monitor all the issues on the pad. We do slope patrols, we do rain inspections, we can find dry spots. It's a really good technology. Everything we learned during operating the Saavedra pad, which has been going approximately, well, since 2006, we have applied all those lessons when we built Lone Star. We've learned a lot. We control access to the pad, so we never don't let anything on the pad that has more than 5 psi. Any equipment that goes on there has wide tracks and so on. And we control, should we need something unusual like a specific drill rig that we can't obtain something that is 5 psi less, we will go through quite a strict procedure to approve that and have a good justification before we do it. We also install drain lines around the perimeter of the pad during stacking. That gives solution an opportunity should we have any high piezometer areas or high solution levels. We have a way for that solution to disperse and possibly leave the pad in a controlled manner. We also install vertical wick drains throughout the pad to assist in solution percolation. So that creates uniformity between lifts. So moving on to performance. So as you can see on the top left, that's one of our residual drills. It's a sonic rig that we bought specifically. We do obviously do mass balance accounting, and we utilize a drill rig so we can drill after leaching and do our recovery calculations. And we can do that very effectively because we know geospatially where every single shift we have good data for what was stacked in that particular area of the pad. That goes back into our GIS database, and we can actually pin down our grade, P80, lots of parameters based on what was stacked there. So it's very useful for doing our recovery drilling. We don't have to put a drill on before we leach because we already know what's stacked there. Drilling requires a permit. We don't allow a drill on the pad unless there's a good reason. And again, it has to be low ground pressure. So some examples on the screen of some of the many KPIs that we watch on a daily basis. For example, there's just our general copper tenor or copper grade in PLS. Acid and RAS are super important. So that's where a high acid consuming ore. And then PAT, obviously try to keep those in parameter. But on a daily basis, we have so many parameters we watch. Let's see. We have a bell cut sampler that is between crushing and agglomeration. So we're able to get very accurate P80s and mineralogy. We take bucket samples or belt cut samples every 2 hours and average those. So we have very fine detail of what was stacked on the pad in a given area on a given day or given shift. So, okay, thank you. Move on. So geotechnical monitoring, again, this is a super high level. I'm going to gloss over this real quick, but the stability of our heat's monitored using a combination of different factors. Obviously, we use piezometers, which monitor pore pressure, indicating solution level. We have survey monuments and GPS units to detect displacement. We have shape arrays to monitor our subsurface movement. And we also use INSAR, which compares satellite images to monitor displacement. We monitor all of these daily, and reports are generated, and a large group of people review them. So we're very, very closely monitoring our stability. Thanks. So successes and learnings. I'll tell you what the chart is first. So this just shows when we were moving from Safford pad to Lone Star, solution balance is really super important. You're turning off an old pad, you're bringing on a new pad with a very fast reporting time. So you've got to watch your solution balance and plan ahead accordingly. We did a pretty good job of that, which I'll go into. But the two important lines on this chart to look at are the two solid lines towards the bottom. Those show the flow delta between RAF and PLS. You see where it goes negative? That was a huge solution outflow from the old pad that had to be contained at the same time as we had new solution coming out of the new pad. So we had many, many learnings and successes during lift one, stacking and operation. First one I'm just talking about was the water balance. So you have to really anticipate what that looks like and take some good estimates and have sufficient storage for that excess PLS so that you can put it back in process and utilize it. We obviously had pretty big ponds. We planned and we coordinated really well for that. We also supplemented with diesel pumps so that we were able to bring that solution back and put it where we wanted to. So as I said before, the leach pad started in February. So that was well ahead of the monsoon season, which in the Southwest, so it was pretty good timing. So it was a good planning on our part there too. And then fresh water, something else you need to really consider. If you're going to be putting in a lot of makeup water, you need to start early and you need to have enough wells drilled, planned ahead in your long-term planning for a new stockpile. Again, we were ahead on that game too, so we planned really well for that. We also considered turbidity could be a possibility from a new leach pad. So we actually put some double drip line on the first few cells so that couldn't hurt us. As it happened, we didn't get any turbidity, which was great. Let me back up here, something I want to cover. So whilst establishing the first lift of crushed material, the stacker started having some lateral stability issues. As it's moving over the brand new ROM and stacking new material, the stacker tracks were becoming misaligned, and then they were tripping out on their safety factors. So then they couldn't stack. And this was happening so often, it was multiple times a shift. So we ended up working with the leaching, coordinated with stacking, and we all collaborated. And we actually put skid steers out on the pad. We had people around the clock watching and actually moving these big boulders and making things how they should be so that stacker didn't have these problems. So we were able to successfully get through that initial lift and those issues with the slightly bigger raw material than we had planned for. Ground observers, 24-hour ground observers on the ground. Let's see. And let's see. Okay, acid consumption. So your acid consumption and downstream effects need to be considered. For an oxide copper deposit, our PLS was expected to have low initial acid, in the PLS because of our column testing that we had done. We really anticipated that, especially also since we were neutralizing that ROM layer, we figured we might be really low on acid. As it so happened, it really did not use as much acid, and we had more free acid in our PLS than we expected, which that resulted in lower pH, which in a copper extraction, that's a negative. You don't want to have low pH. So we had to compensate in the SX. And again, we collaborated with the SX people. Yes, we saved on acid because we didn't have to add so much, but we had a little bit more extractant so that we could compensate in the SX. Some engineering piping designs didn't quite meet the flow needs when stacking the north end of the first lift. What we discovered was the flow was designed to feed an equal number of cells in the original design, 18 cells, right, split 3 ways. That the effect of hydraulics, because the flow goes downhill to the bottom of Lone Star pad, the flow was biased. And so it was pulling from the north end of the pad. So we ended up having to move the isolation points of the lines so that we could get more equitable flow distribution. And that was quickly remedied. We got together again, engineering, operations, leaching, everyone collaborated to make that engineering change. And then also a flow discrepancy was discovered between the individual flow meters on the modules. That's the skid flow meters, which are a discharge pressure flow meter, and the mainline magnet flow meters, which fed the pad. If you summed them all up, they didn't match. That's not a good thing because we really want to know what we're putting on our true application rate to each module. So we quickly got with the vendor and collaborated again and came up with a method to put a factor into each skid electronically. And so we went through and reconfigured every single skid. So now the flows are less than 1% delta. So it's, again, a good example of collaboration. And so, well, in summary, between our engineering groups, technical groups, operations, we all work together as one big collaborative team to solve these challenges and in the design process. And as a result, we've been able to completely maximize our tank house and exceed all expectations with leach recovery on load stop pad. So big success overall. So.
So we just heard that our next speaker won't be available, so we got time for lots of good questions for Pip.
Okay.
Yeah, hi, great presentation. What is your average application rate?
0022.
002, okay.
Hi, thanks for the presentation. Just on the offloads, you guys did common offload for all cells to PLS. There was no, you guys didn't consider splitting the active cells, dead cells, just to increase PLS grade?
No, we just kept the two pads completely separated.
Okay.
This is Shiji Wang from Core Mining. It's a very good presentation. Show a lot of practices and start points. My question is that when you mentioned your flashing, the picture you showed of flashing, what is the problem with your flashing? Because of scale up in your pipes, you're flashing?
Well, rain events generate turbidity, as we all know. You can contaminate your PLS with turbidity, which can build up in your SX plant and create crud, which then can cause crud runs in the SX, or gunk runs as we know them. And that also comes back out to your leach pad. So any SX buildup of crud can cause a gunk to come out of the plant, and it goes straight to the RAF system. Then it'll plug up your emitters in your leach pad. So we try to control the rain events, we control the crud runs by minimizing the turbidity to the SX plant in the first place, and minimizing the turbidity to the leach pad. But by having the flushing valves opening twice a day for about 5 or 6 minutes a piece, we flush everything out. That's the solids, any organic that comes out of the SX plant that could potentially cause plugging in the emitters.
Have you got a chance to see any build up in your pipes inside or not?
We get plugging throughout the leach cycle. I don't think there's a site anywhere that doesn't have some form of plugging. But typically, you're looking at less than 10% at the end of a leach cycle, unless you've had some event, a triggering event where you had a lot of turbidity for several hours and you weren't able to increase your flushing system. The one thing that we can do, since our flushing system's fully automated and radio controlled, is we have control by the water balancers and the metallurgical group. If we have a rain event or we know something's going on in the SX plant, like turbidity, gunks coming out the plant, they've got a plant upset, some kind of instability, then we'll go in the system, we'll double up or triple up the flushing, and it's pretty easy to do. So that instead of having your 2 5-minute flushes, suddenly you've got 4 6-minute flushes, or whatever you want to do. You can pretty much set up that system to do anything. As a result, we've been able to mitigate a lot of potential turbidity issues, and we can run higher turbidity to the leach system and actually through the SX.
Yeah, because turbidity meter is a very trick. Is only ppm level, and you try to control that. That's not easy to do. Yeah, good job. Where's the flush water to go?
We have perforated HDP corrugated lines coming off each valve, and they distribute out across the pad, and the turbidity is punctured a hole so it can disperse that solution, so it's not dumped into one spot and creating any kind of issue from a geotechnical perspective.
Okay, yeah, thanks.
It's a big room.
And we've got time now, right?
Hi, Pip. Good presentation. I was just wondering, you're doing is it belt agglomeration for the ore?
I'm sorry, could you repeat the question?
Is the agglomeration for the ore that you're stacking, is that belt agglomerated or are you using agglomerate?
Oh, agglomerated drums.
Okay, so what then is the reason for your 2 feet or 1 meter of ROM on top of your solution collection drainage
I
layer?
think part of that was, so your coarse ROM and fine ROM layer is to protect so that the stacker doesn't damage the liner. It's also used to bed your HDPE collection system piping.
Okay, so, okay, that answered that
It doesn't, I mean, you're not going to filter the turbidity or any of that stuff with that kind of thin layer of ore.
Yeah, but it ends up as a huge cost to your leach pad, putting that 2 feet of ROM material on top of it. I
Right.
assume it's ore bearing.
It is. It's
Coarse ore.
coarse ore, yeah.
Yeah.
And actually, we have one of our design engineers, Michael Grasses, in the room, so Michael might be able to speak to that.
Yeah, it's primarily to prevent liner puncture or damage to the piping collection system, right? It's the stacker system has about a 26 PSI ground pressure load, which it travels multiple times over one area. And so on that first lift, we run the risk of just crushing all of our pipes just with the stacker system. And so that extra 2 feet of material reduces the ground pressure at the level of the piping and on our liner system.
Well, thank you for giving me the opportunity to present today. Thanks, everybody.